This is the Air and Space Museum in Washington DC. There's loads and loads of cool stuff around, and I figured since you guys are studying all this just now, that I'd try and come up with a weirdo problem for you here. So, this is all about moving into space. Now, space starts 100 kilometers up, according to international law. But even there, the atmosphere is thick enough to drag down spacecraft. So, they must be 362 kilometers above the Earth's surface in order to stay in orbit. So, you know the value for big G, you've got to figure out how high that spacecraft, how fast that spacecraft must be travelling. So we have two questions here, one on escape velocity and one on orbital velocity. This is the first question. So what I want you to try and figure out, I want you to figure out the velocity at which something will need to travel, in this case a rocket, in order to escape the gravitational field of the Earth so that it doesn't fall back down. So, what velocity must a rocket travel at in order to reach its escape velocity and not fall back down to Earth? Here's the data you're going to need. Big G, gravitational constant, the mass of the Earth, and the radius of the Earth. What I suggest you do is pause the video, take a few minutes, have a stab at the problem, and then press play again. Off you go. So here's the solution for the escape velocity problem. The key in this case is realizing that it takes a certain amount of energy to overcome the gravitational energy, or you really need to gain gravitational energy as you move away from the field. In order to do that, you're going to need to convert some kinetic energy, so the two have equivalence in this. So we're going to use both of these equations to help out. Now, the kinetic energy equation is pretty familiar by now. The gravitational energy, if you forget that exact equation, or you can't find it in the equation sheet, it's derived from Newton's universal law of gravitation. So F equals gm1m2 over r squared. And work done equals the force times the distance. So if you substitute for force, you'll cancel out one of the r's on the bottom, so it's no longer r squared, and you'll get gravitational energy equals gm1m2 over r. Now, a bit of algebra here, we can cancel out the m's, and then it's simply a case of rearranging the equation to suit your needs. So we figured out v equals the square root of 2gm over r, which is the equation for figuring out escape velocity. So you can figure out on any planet if you know the mass of that planet and the radius. So for example, escape velocity of Mars is a bit lower because it's lower mass. Then we can figure out plug in all the values for g, m, and r, and we figure out the escape velocity for Earth is about 11.2 kilometers per second. This is the second question. This one's on orbital velocity. This is a picture, well, it's a GIF really, of the International Space Station flying over what I think looks like Florida. Could be wrong. And we're trying to find the orbital velocity of the ISS, which usually orbits around a height of 400 kilometers above the Earth's surface. So what you're going to need to do is, using the data you had previously from the radius of the Earth, the value for big G, you're going to need to calculate the orbital velocity of the ISS, a height of 400 kilometers above the Earth's surface. Pause the video, take a stab at it, and come back. And here's the solution. So, in this case, we're looking at force, because centripetal force is pretty familiar, especially from Unit 4 of A-level. And gravitational force, which in this case are equivalent. So, we've got Newton's universal law of gravitation and the equation for centripetal force. It's pretty straightforward. Then we use a bit of algebra, we get rid of the masses. Then there's no need to divide both sides by r. So we score out r on the centripetal force, and we take away one of the r's from gravitational force. Then it's simply a matter of rearranging this equation to suit your needs. So orbital velocity is the square root of gravitational constant times the mass of the Earth over r. Therefore, The key in this part is remembering that G and M are both pretty straightforward, just plug in the values, but R in this case is the radius of the Earth plus the height above the Earth's surface that the ISS is travelling at. So ISS is 400,000 meters above the Earth's surface, so we add both of those values together. We figure out that ISS will be travelling at 7 kilometers a second, roughly.